All right, I'm going to ask if somebody's out there and confirms that you can see my screen and that you can hear me.
Yes, ma'am.
Okay, thank you. All right, before we get started, and so this is back to, what is this, lecture 3? So we're still in lecture 3. And we just finished this problem. What did it look like? We had heat addition at nodes of our resistance network. And again, the kind of interesting thing I think about this one is I always think about resistance networks is we never want to have heat addition. And we still can't write a whole node, you know, a resistance network across this whole system because the heat addition makes that invalid, but we can write it at certain nodes. Okay, and I got to come up with the problem, so you get to try it once. We kind of went through this one, but you haven't tried it. Okay. So in just a minute, we'll start this problem. Okay. I keep having this announcement and I forget to make it. Do you recall it was your first homework set and I asked you to look at some student work and it was taken from a different course, not this course. So it was just some problems from 2 students. And one of the students, I loved grading his homework. And some of you wrote that he was verbose. Anyway, I just thought that was funny. That, you know, so it's like, you know, need to be more concise. And I'll tell you, I found his homework pretty easy to grade. You know, I could follow through steps. You know, the handwriting wasn't the best, but to me, it overrode, you know, that he spread stuff out that had all of the, you know, all of the steps listed in there. And I think in general, the people thought it was okay. You just thought it was maybe too long. And my other thing would be, you know, when students hand in homework, people would have like 5 sheets and this guy hand in like 20. But it was like, I knew what I was getting. Anyway, not necessarily encouraging all of you to follow that mode, but just telling you I probably sway more towards the side of finding it easier to grade homework when you have more steps explained than these really concise homeworks. Somebody asked about engineering equation solver, EES. Okay. You will likely have to ask me some more questions, but this is what I know from now, is that there is a way to download EES from the engineering software bundle, engineering software bundle. That's at the U of L. It will be in the Speed IT website, and I can give you that information. But I'll tell you that you need to be on the U of L network. So you have to be on campus. If you think you want to come to campus, and I'll tell you guys, I was thinking about it from your perspective. I think our library is really nice. It's got good air conditioning. It's pretty big. It's pretty quiet. You know, if you came to the library sometime to work and you're perfectly fine, you would be on campus. You could use ease. I'm also making a pitch that we have student rec center. So to me, it's a pretty nice gym facility. Again, I don't know that you want to study there, but you could study there and then get a workout. So you could be on campus and there may be a reason why this works for you. So let me know and I can send you more links or it's probably not too hard to find again if you went to the Speed IT. But I think that is not what most of you wanted. I think you were hoping that there was a way that you could use it remotely. And if you're thinking back probably a year ago, somebody who really wanted ease to be part of their course, they went through big hassles with getting VPN accounts for each person that wanted to use it. And Speed IT just is not going to do that again. So I'm telling you the options. If you want to be on campus occasionally to use ease, there's a way to figure it out. If you want to use it at work, you are going to have to, I don't know, work with Carlos or whoever else gets you guys access. Okay. My third note is that I have nearly finished, well, I actually finished review paper number 1. But I haven't given you grades, so you don't know that's out. I got to figure out how I'm going to put in some feedback to you. Okay. And I graded it out of 20 points. Okay. And that really has no bearing. I think in your overall grade, it's going to be between 2 and 3%. I think I have, no, maybe it's 3%. 3 papers. But let's say it's 20 points. And I'll figure out what percentage when we get to the end of the semester. The thing I was going to say is that if you got a 19 or a 20, I sometimes didn't give you any comments, and I hope it's not super frustrating. But as I'm reading through, sometimes the people who had 20, I was like, bam, I just can't even see anything I would criticize. And sometimes with 19, it's like nitpicky stuff that I just don't think is quite as clear. But I hate writing. I shouldn't say I hate. If I had paper copies, I would maybe say this part seems unclear. But in this mode of operation, it's a little bit tricky to type out what I'm saying. So 19 or 20. I maybe didn't have some real, 20, I didn't find anything. 19, I might probably found something. I just didn't think it was good as a 20. Once we get down to 18, I will list some things like you had, a typo, I don't care. But when I see a couple typos, I find it distracting. Or I just didn't think it was organized in a very logical format. You say a sentence about one thing, and then you got a sentence about something else. And then, I like it. Some people did a very nice job with, I think, paragraph structure, that your paragraph kind of flowed, made a certain coherent point. And so just so that you have some idea, if you see a 19 and you don't see anything written on it, it was probably, I just didn't think it was quite as good as some of the other papers I read. We have been talking about resistance networks, and this picture is really going back to a resistance network with nothing special going on. We've got isotropic materials, so thermal conductivity doesn't change in a direction. We don't have volumetric heat generation. It's back to the old stuff. But this is a pretty good figure to talk about the idea of parallel path method or isothermal plane method as a way to set up a resistance network. In this figure, these surfaces are insulated. So they drew them as dashed lines. I often do these dots. So no heat's leaving, no surfaces. And I have a certain temperature on one face and another higher temperature on the other face. So we picture heat flowing through these materials. And it's a composite material. So made up of some chunks of material. This is Ka. Oh yeah, this one got too dark, so you can't see. All right, so this is material C down here, and this is B, so Kb. And so we know thermal conductivity for all of these materials. And I just wanted to be clear that Kb and Kc, these thermal conductivities for these two chunks of material are different. They happen to be pretty significantly different. And nothing's changing out of the page. So just a conduction through these chunks of material. Parallel path method has another name. I like parallel path method better, and you're going to see why, but just in case you read this, another name for this is adiabatic resistance limit. And parallel path method would look like, I picture I have a temperature node over here and a temperature node over here. And heat that starts flowing through material B, I'm going to show it first goes to material A, then material B, then material D. And that is in parallel with, if I have some heat packet of heat, some energy that starts passing through material C. It stays on that same path. It's going to go through A, C, B. No, C. Sorry, I messed that up. A, R, C, and then RD. And so you can picture some of the heat going through one path, one going through this other parallel path. Okay, and this is the picture for parallel path. And I like this name way better, adiabatic resistance limit. I can sometimes think through why that name makes sense. Okay, the other one is isothermal plane. An isothermal plane you want to think about is each place I move to a new material, it's a uniform temperature. So for example, I have some known temperature, T1, and I could put maybe a T2 here. So isothermal plane would say I got cold here, and it all goes through to material A. But now, once I get to T1, now these packets of heat can determine whether they'd like to go through B or C. And I don't mean to, like it can decide, but you can think about it. If one has a lot more thermal resistance to it, then maybe a little packet that was heading this direction will decide it's going to be easier to get through C. It's got a lower thermal resistance. So it chooses one of these pathways. Okay. And now we'll get to another plane of constant temperature. And now all of that heat has to pass through that slab of material D. These two thermal resistance networks will give different values for thermal resistance. So if I summed up for the top and I put RA, B, and D in series, so I'm adding them up, RA, RC, and RD in series, and then I put those two paths in parallel, I get a thermal resistance of 0.32 Kelvin per watt. If I summed up the isothermal plane, thermal resistance is 0.50. It works out that parallel path method will always give a lower thermal resistance. And this was just a given example, but no matter what we picked, it might be a really small difference, but it will always be a little bit lower. Okay, let's do one more thing. So they told us or the temperatures on these two faces. So if I calculated heat transfer through this, you can picture that the rate of heat transfer through the parallel path method is going to be larger since it's got a smaller, we're thinking Q is delta T over sum of thermal resistances. So this Q would be 313 watts, and this Q is 200. If you are thinking back to your first heat transfer class, and I bet you did isothermal plane method and didn't even think about this other option, parallel path method. And it was a couple years until I actually taught a different course where I even thought about these two alternate ways to model a thermal resistance network. And the real situation is between isothermal plane method and parallel path method. So somebody ran a finite element code, put these boundary conditions in. I know these temperatures, put these materials in, and no thermal contact resistance between these material boundaries. And you get a Q of 282, so in between these two cases. And the reason that neither of these resistance network models is perfect is that if I were drawing heat flow lines through this, so I have these material A and material D. And then I have material B, which has low thermal conductivity, and material C, which is hot. So it's going to be able to transfer heat. If I were drawing heat flow lines, I might have something like, so we're heading this direction, but I can see that this is going to be a simpler pathway. Okay, so flow that's in the upper half might go through material C. And thermal resistance network is based on one-dimensional conduction. That's one of our assumptions. And through these materials, it's not one-dimensional. It's not only in the X. We've got some transverse heat transfer. And so we don't do a perfect job. So our estimates may be okay. And in particular, if we don't have such a dramatic difference between these two materials, B and C, we might not see that much difference in these two paths. But this problem was made up to show a little bit more significant difference. This next problem, when we meet in person for class, I usually have students work in groups and solve this problem. But that's not going to pan out. So I'm going to show you a little bit. We'll set some of this up. There really isn't too much interesting about this problem. You get to see some different types of resistance networks, different terms that go together in the resistance network. The thing that I think is interesting is this has radiation going on the outer surface. And we talked about radiation involves a surface temperature, and we don't know the surface temperature. So just a chance to think through how you could handle that radiation with that unknown temperature in there. Okay, this has a lot of details to it, but they're saying we've got this spherical shell that contains liquid oxygen, and they tell us the liquid oxygen is at 95.6 Kelvin. And then they give us a whole bunch of information. Let me see. I'm going to go ahead and sketch out the resistance network and not read through all of these details. But we have, from this inner surface, I'm going to start from liquid oxygen. There is a convection coefficient. And then we have a metal liner. There is a contact resistance. There's insulation. There's another contact resistance. There's another metal liner. And finally, that is the outer surface of the tank. They tell us that the ambient temperature surrounded by air at T infinity of 20 degrees C and radiates to surroundings that are at 20 degrees C. So our air and our surrounding temperature are the same. But this is a parallel path for heat to be actually coming through. So where it's this liquid oxygen is much colder, so I've got Q coming through to the liquid oxygen. So if we started writing down thermal resistance elements, and we're thinking Q is, we know the delta T, sum of thermal resistances. We're just going to start cranking through and calculating thermal resistances. For convection, the form looks like 1 over heat transfer coefficient and then surface area. And so we got to look through and see where they give the convective heat transfer coefficient. Let's see. The heat transfer coefficient between oxygen within the door and the inner surface is 150. And then one of the difficult things is usually figuring out surface areas, but I'm going to remind you surface area for a sphere 4 pi r squared. So you got to figure out what radius you're at. All right. But let's say we know everything. We got those too. For the metal liner, this is a conduction resistance through this, albeit it's a thin layer and it's metal, so it's probably pretty small. But that would look like 1 over R1 minus 1 over R2, 4 pi K. Okay. And this is going to be K for the metal. And you got to look through. This is showing it a blow up of what the wall looks like. And so you got to figure out what radius 1 is, which would have been, and then the thickness of the metal layer to get R2. The next one is a contact resistance. And if you read through in the problem statement, what they give is the normal form of how they give a contact resistance. Okay, and it's right here. So it doesn't have our typical units for a thermal resistance. It's got an extra meter squared in there. So we got to remember to divide by the surface area. And that's going to be for area R2. We've seen most of the exciting or different parts of this. I'm going to say insulation. That's going to be back to a conduction resistance. So 1 over R2 minus 1 over R3 to get the thickness of the insulation, and 4 pi. And now this is going to be K for insulation. Okay. And I know you haven't read through all of this problem. All of the details are given in this. So we do have K for insulation given. Yeah, it is this one, this wacky one of microwatts per centimeter Kelvin. Okay. Okay. Contact resistance, we know how to do that one. We got to make sure we are using that area at radius 3 now. The metal liner, we've seen how to handle that. It's another conduction resistance. Let's look at radiation.
What is the RTC prime again? Or double prime?
What is the RTC double prime?
Yeah.
Okay, thermal contact resistance.
Okay.
It is given in the problem statement. So and I know I did not read through all of it, but if you looked a little bit later, it's given right there. And you're imagining that I don't have perfect thermal contact And because I have metal layers, that they're saying this contact resistance might be significant. I should probably include it. It might be on the order of these metal liners. So this is the one where once we get here and we realize, we're given the liquid oxygen, we know T infinity, so we know most temperatures. We don't know that surface temperature. So one way to attack this is to guess what this temperature is. So the other day we had this approximation. And it's for a relatively, so not such a big temperature difference. I'm going to say, I don't know what this T surface is, but I'm going to say it's not that much different than T infinity. I'll just put, or T infinity / T surrounding. I'm going to put T surrounding in here as my estimate. So just so I can get a starting place for what this resistance, thermal resistance due to radiation might be. Emissivity is given, sigma, that's a constant. Oh, I should be putting my checks down here. And we're going to guess 20 degrees. Yeah, 20 degrees C as our T infinity - T surroundings. We're going to put that in. And then what do we need? Oh, we need our convection out. Okay, and the surface area changes again. So we got to be making sure we put the right radii in. That was half the battle in this problem. Okay, and then our combined. Nope, let me do a new name. R in parallel. See, these two are parallel. So the way I'm going to handle this, now I can finally put together all of these thermal resistance elements. Okay, and I did not do a good job of setting this problem up, because I'm going to tell you, if I scroll back, it says, oh, draw a thermal network. We did that. Let's solve for rate of heat gain by this vat of liquid oxygen. Okay, so let's say we're going to solve for Q. Okay. We know delta T, so that was working all the way across this thermal resistance network. And let's say we summed up our thermal resistances. So we got this guy and we got that one. Okay. And my point was going to be, we are not quite done. We guessed what to use for our average temperature to calculate a radiation heat transfer coefficient. But we didn't know that. But now that we've made a guess for T, we can calculate Q. Now we could calculate TS, the surface temperature. So picture, I'm going to scroll back up, and I'll be back down here in just a minute. In my thermal network, if I know Q, that passes through this whole network. I can now use that Q, and I think the easier way to do that is I've already solved for all of these guys. These aren't changing. Is to do all of these resistance elements. I'm going to work from here to here. And I can solve for the surface temperature. So I want to rewrite this equation one more time. We didn't know it. We did some way workaround to make an estimate of it, but now we could solve for it. All right, and already I don't like that because that's going to give me a negative sign. Liquid oxygen's way smaller. So let's just go ahead and reverse that order. And now, and I will not remember all of these, we want to do our convection in. Our metal liner on the inside. Contact resistance on the inside. Insulation. Another contact resistance on the outer surface of the insulation. And metal liner out.
A quick question.
Yes.
Are the actual values for the R metal liner in versus out, or the contact in, contact out, are those different?
Yes, they are. And it's because the surface area is different.
Gotcha. That makes more sense. Okay. I was curious as to why we weren't just doubling them, but I forgot it was a circle.
Yeah, and I think I was not. So, I mean, they look like they're the same up here. But when you run through the numbers, because they have areas in them.
Right.
Okay. So I've rewritten this equation, and our whole goal from this is I'm using that Q that I had. I just came up with the Q. I'm using that here. These are all the values I've previously calculated. I know for liquid oxygen, I'm going to solve for surface temperature. All right, and this is where you would be happy if you put this into a spreadsheet, because you wouldn't have to keep calculating these things. So I could go back through and I would update my H sub R. So we had to make an estimate for it, but now I can put in that surface temperature.
Dr. Priab,
Yes?
should the parallel resistance also be in the denominator of that Q equation?
That I have just written?
Yes.
Okay, no. And you're giving me a good chance to hit this one more time because I've been scrolling around too much, likely.
Okay.
So we're working from surface temperature to liquid oxygen. If I look back up here,
You're
I'm
right.
only working. Yeah.
Okay. Thank you.
Sure.
And then why wouldn't you use T infinity instead?
T infinity here.
Yeah, instead of the
Yep.
T liquid, like go the other way and use the parallel resistance instead.
Okay. You know, the reason I think is because you've got this unknown H rad, or this guy in it, which we're trying to recalculate. So to me, you could do it the other way. You could do it the other way if you're thinking, you know, I would just work across this section. But because this is the term we're still working on, these other resistances, even though it's longer, it's all the same thing. So to me, it was easier to work that direction.
Okay, thank you.
Okay, so in my steps, what am I saying? So we solve for T sub S. We can recalculate H rad. We can recalculate and again, that's going to be the total. That's going to be involve the two resistors in parallel, since we've gotten this new radiative convective heat transfer, or no, radiative heat transfer coefficient. Okay. Now we've got this new thermal resistance. We got our same delta T. We're going to recalculate Q. Let's see. I went through this process 3 times of solving for a TS, getting a new HRAD, getting a new sum of thermal resistances, calculating the new Q. And I stopped, and I'm trying to give you some kind of indication. Yeah, my first time through, oh, okay. So let me show you this. So first iteration, when I used my estimate, HRAD was 4 watts per meter squared Kelvin. And then I went through in my second times. Was 3.21. And the third one, and I quit. And this is probably more than I think. Well, I'm just seeing that it really quits changing. So my third time through, just changing in the 100th spot. So I'm done. I'm going to use this value in my calculations, and the heat gain by the liquid oxygen is 69.5 watts. All right, so that was a lot of cranking through numbers. One of the things I would like you thinking about is the issue of this radiative heat transfer coefficient. That I always think it looks just like another resistance element, but because it's based on knowing surface temperature, if I look back up here, surface temperature, sometimes it throws an additional complexity into the situation. Right? And the way that I got around it is I'm making some guess and I keep iterating through the problem. Okay, and if you're concerned, this is usually not a problem where you have issues with it converging. It will converge. I think that is it for talking about thermoresistance networks. And then I am ready to move on to lecture 4.
Hi, Dr. Bree. I have another question.
Yes.
So what did you do for the third calculation? What estimate did you use?
Okay, I'm not sure I got your question yet, but but I'm scrolling down to where I think you're heading, or where.
Yeah, so I followed how we did the first iteration. You approximated using T.
Oh, I just said I'm going to guess T infinity is equal to T surroundings to use in that estimate.
Right, and then you went back for the second calculation and solved using the left-hand side of the network. For the third calculation, what did you do? What was your?
Once I've got a surface temperature the first time, the third time I'm going through the same thing. I'm going to get a new surface temperature. So I put this in. Let's see, where did we do? So we recalculate a Q from this second iteration. I've got my new HRAD. I get a new sum of thermal resistances. I recalculate Q. And now, just like I did up here for that third calculation, I'm using that new Q. I'm using all of this stuff that's, and I'm going to use my red pen because I'm circling stuff, but you don't know what I'm circling. Okay, so I've used my new Q. All of this stuff stays the same. This stayed the same. I'm going to solve for a new T surface. And now I'm just following through these steps again. So to me, except for the very first time when I had to figure out some way to get an estimate for this, after, I'm always using my new surface temperature in this equation to get the radiative heat transfer coefficient.
Okay, got it. Thank you.
Okay, so this would be lecture 4. And we are going to talk about fins. And another name for fins is extended surfaces. there is a reason why this topic fits into conduction. So this is still in chapter 3 of your textbook. And I, at first I always think, man, why would that be? Because I picture the convection coefficient, and I've just written down this Newton's law of cooling, and we think about having a fluid pass over these thin surfaces, that it's a Newton's law of cooling kind of problem. But the analysis, the simple analysis we're going to do is a conduction analysis, and we're going to set that up in a minute. I have these pictures here so you can think about some different thin surfaces. So this is a motorcycle engine, and the combustion chamber may have thin surfaces. And for motorcycles, that may be exposed, as you're running down the road, exposed to ambient air. This next picture, if you have, this one is common, at least in older computers, like a CPU unit, and it's got these hooks to try and have a nice fit, so it sits down on top of the electronic component that it's trying to cool, so it just gives a nice force fit. This one is from heat recovery steam generators. So if you had a gas turbine and you have some high temperature exhaust, you may extract some more heat from it. And these are pretty beefy kinds of heat exchangers, but have tons of surface area. And then this last one is a Stegosaurus. And there is this idea that the dinosaurs were so large that to be able to get heat removal from their bodies, that they might have had bodily fluids that are passing through these plates, sort of thin surfaces on their, along their back, because you got this good path for heat removal. It's near the surface. Okay, so we want to talk about this real quick. So here's my basic equation. So if we want to improve rate of heat transfer, things that we can do, we could improve H. So it could make heat transfer coefficient higher. That means you're maybe going to have to blow air or pump water or some kind of fluid over the surface. So you could do that. That's one option. Another one is that I might increase surface area. And that's the one that fins address, is that, and this one's easy to think about, if I am removing heat from this base area versus all of these finned surfaces, you can think through that I have, 10 times or 20 times more surface area for that thin surface than just the base area. Okay. And then the third thing you can think about is you could decrease the fluid temperature. But often you're going to try and use something that you have available, like river water or ambient air. So paying to cool the water below ambient temperature has some costs associated with it. So in practice, there is a reason why sometimes this idea of increasing surface area and adding a fin might be the cost-effective way to get more heat transfer. All right, this is a generic picture that comes from your book, and this is showing an example of an extended surface or a fin. So it's attached to some base surface, and we are going to do an energy balance on this little orange section, this differential element of the fin. We make some simplifications in our fin analysis. We're always going to look at constant properties, and that just says that K is going to be isentropic. I said isentropic, and I apologize, isotropic. It doesn't vary in direction, it's just one constant value. We only look at a steady state analysis for fins, no volumetric heat generation. Okay, and as our picture is drawn, they have X moving away from this base. Oh, here it is. Let's look at that X coordinate down there. That we only have conduction in the X direction. Okay, so a way to think of this, X direction conduction only, and I'm going to make my sketch from side view. So this is my fin surface, and I didn't draw it like they did. They've got it changing cross-sectional area. I've just got this slab pointing away from the wall. Okay, and you can imagine that I have convection, so I got heat leaving this fin. But X direction conduction says that at each point, I'm going to assume temperature is nearly constant. So if I was drawing a temperature profile across this, oh, maybe I should be drawing it like this. Let's make that whole thing a temperature profile. So that relates to temperature. And if I took a slice here, maybe it's cooled off some. So my temperature is a little bit smaller, but it's only a function of X. If it were a function of X and Y, then maybe my temperature profile that's getting cooled down on the outer surfaces, maybe it looks something like that. Ooh, that's really cool. But okay. So now it's varying with X, but I'm also seeing, if I put my X here and I'll put Y here, that I have some variation in the Y direction. So we want this case, not where I have my temperature would be a function of X and Y in this case. We've already assumed no volumetric heat generation in the fin, and we're going to look at steady state, so we don't have a storage term. And now we're just following this diagram that they gave us up here, that we've got Qx coming in. So we're thinking that's conduction into that little element, that little slice. And leaving, we've got dq convection and leaving Qx plus dx. Okay. I'm going to rearrange this just so I can follow my notes. And so I put these negative terms on the other side of the equation. So what am I doing next? I'm expanding this out. So I'm going to write this as qx, and this next guy is qx plus, and this is how qx varies in the dx direction. Okay, and we're showing this little slice has a thickness dx. And dq convection, we're writing that as yep, there they have it. Okay, so we're looking at convection off of this cylindrical surface. So it's a heat transfer. They're using a differential surface area. And then this is going to be temperature minus T infinity. That looks like convection. You can already see that since these are on both sides of the equation, I could cancel those out. I'm substituting in for qx in terms of Fourier's law. So minus k, and I've got a cross-sectional area and dt dx. And I'm going to put my little note over here. All right, and I'm just repeating this h das t minus t infinity. All right. Okay. I am going to go ahead and take k out in front, since we're going to say constant properties, and okay, and then I'm going to divide through on both sides. So I'm going to have 0 d by dx ac dt dx. But now I took that negative k out in front, and I'm going to divide through, so I got minus h over k. Okay, I got another bad thing, but let me finish this off. DAS t minus t infinity. Okay, was anybody getting ready to tell me? And I only feel bad if you're like really questioning. All right, so I said I canceled these two guys, but I have a d by dx, qx. I need a little dx back here. I dropped that. So I'm going to try and squish it in here. Ooh, minus. All right, we already talked about that. Okay, and many times I like our book a lot, but this one's a little bit unusual. I'm going to divide through by dx, and we want to think about, this is not a derivative with respect to x. This is our little element length dx. Next thing I want to do is expand this first term. Okay. On the right-hand side of this. So 0 equals. So I can take derivative of cross-sectional area with respect to x, and then I have dt dx plus cross-sectional area, and then d squared t dx squared. And I'm leaving the second term the same. Okay. All right. At this point, we are going to drop this first term. And the explanation we're going to give is that our first look at this, and we'll relax it later, is we're going to say we have uniform fins, uniform cross-section fins. So if I have a fin I'm going to analyze, maybe it is a pin fin. So it's a cylinder, and this is my wall. Not a good job drawing it three-dimensionally, but it's got a uniform, it's cross-sectional area doesn't change with x. Or I could do, this one's easy for me to draw, if I had a plane fin. So it's just a slab of material, its cross-sectional area doesn't change with x. So for constant cross-section fins, this term drops out. I'm scrolling up to my picture up above just for a minute. All right, this picture, they showed that cross-sectional area is decreasing. We can't analyze this using the equations that we're coming up with right now.
So if we ever get a case, I guess, for your class, and we are shown, would we just not be shown that changing cross-sectional area so that we can make that assumption? Because I wouldn't assume, I wouldn't make that assumption if I had seen that other image first.
Okay, so that is the general case. And eventually we do have some fins that are they have to be certain mathematical cases, like a parabolic fin. So we can handle some cases, but for right now, we're going to do more development with this uniform cross-section. So if you're concerned, I'm going to say, that was a general picture. They started out with that, but just know that these next sets, and you'll know, it will say uniform cross-section fins. You'll know when you have to assume that, or when you, we don't do the development. I'll just say I won't show this detail of development when it's non-uniform cross-section, because the math gets much harder. That helps it all. But you're okay with this idea now. I mean, you know what kind of fins we're looking at. That any slice I take in X direction, I would always have the same cross-section.
Okay, yeah, no, that makes sense. That makes sense for this.
That's okay.
I was just concerned about making the assumption out of the blue, this is going to be a uniform fin. But if I guess if we're told we have uniform fins, or at least given a diagram, then it makes sense.
Yes. Okay. You will. All right. So what do I want to do next? Okay. So we've got this DAS. So that's surface area, how surface area changes with the X coordinate. And for a uniform cross-section fin, the change of surface area with x is equal to perimeter. All right, so let me, I don't know, I always have trouble thinking about that one, but here's my example that maybe can help. So for circular cross section, okay, so we're thinking of this pin fin, circular all the way through. So surface area is pi times diameter times x. So here's my x length, diameter. And if I want a little chunk, a little surface area, I'm taking the dx, and then I'm just forming this ratio. Okay. And so in that case, it's the circumference of this, but hopefully you can think through that that's the perimeter. I take a slice through this and I look at what my perimeter for the shape of this pin or this fin is. So we're going to substitute those things into the equation. So now my equation looks like all right, I'm nearly out of time. But let me do two more things, and I promise it won't be too much longer just to get to this form. Now I'm going to divide through by AC, cross-sectional area. And then let theta equal t minus t infinity. So the theta dx is equal to dt dx, and d squared theta dx squared is d squared t dx squared. So my equation is now going to be converted to look like all right. And this is the part I'm going to stop because I'm going to say, so we've got this ordinary differential equation, and this maybe been a while since you have seen it, but this is kind of a classic one that you would have seen a solution to. So we say we got this ordinary differential equation. It has a solution of a certain form. So we're going to just write down what this solution looks like that works for this ordinary differential equation. Okay, and I'm sorry I didn't get very far, but we hit most of the math. I'll show you the form next time, and we'll see what we're heading towards. You see, I just can't quit quite yet. We're going to come up with, here's our thetas. We're going to come up with some equations that look like these temperature distributions in this chart. Okay, I am going to quit now.
Real quick, if you scroll up a little bit.